In this paper, we present a machine learning approach to detect the user's intention in mid-air sketching tasks without the use of any external interrupts. Drawing curves in mid-air is a fundamental task with applications to 3D sketching, geometric modeling, handwriting recognition, and authentication. Mid-air curve input is commonly accomplished through explicit expression of the user's intention to start and stop sketching, typically via hand postures or button press operations on instrumented controllers. In applications involving 3D sketching, this intention is the differentiating point between a stroke, or what a user wants to draw, versus a hover, a curve that is not intended to be drawn. Our approach is motivated by first studying the effects of spatial input techniques, in our case hand postures, on the intuitiveness of mid-air sketch input. We developed 3 interfaces using the Leap Motion controller, enabling users to draw curves based on a specific hand posture or based on the hand trajectory's proximity to a fixed virtual plane. Finally, we observed the changes in curve input behavior in the third interface where no such external interrupt is required. We find that while robustness of posture detection is a problem associated with camera-based controllers, users find it comparatively more intuitive to draw in the third interface than the first 2. We also observe differences in the trajectory speeds when users navigate a stroke or hover curve, with the hover trajectories being traversed faster as compared to stroke. With this information, we develop a classification model based on features comprising of the inherent geometric and temporal structure associated with the hand movement in the event of mid-air sketching. We collect 3D sketching data using the Geomagic Touch haptic device with an accurate demarcation between stroke and hover curves, and use this data to train and test our classification model. For every point belonging to a 3D curve, we extract its local motion, curvature, and Frenet frame properties and train a binary classifier to predict if the point is supposed to belong to a stroke or a hover trajectory. With this model, we explore 3 different classifiers and test them on different categories of the recorded data and identify a random forest to perform with the highest accuracy. With further hyperparameter exploration, the random forest model predicts stroke hover intent with an accuracy of 78%. With the model's current accuracy, we believe it is possible to create interesting applications like interactive art, especially for large displays. However, for precise applications like 3D design, our approach needs refinement in predicting real-time 3D curve data. In this paper, we presented an approach for capturing user intent while creating strokes using spatial input. In the broader domain of mid-air curve input, our work opens a new problem context that can potentially lead to novel approaches for enabling users to express visual ideas through spatial interactions. Thank you for watching.